Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
I am an extreme-scale computational mathematician that conducted stability analysis of finite difference approximations of partial differential equations of calculus. I conducted those stability analyses in the early 1980s and in Washington, D.C. I computed my Courant numbers that yielded a priori the stability conditions or the time step restrictions for my petroleum reservoir models, simulations, or general circulation models. As a research computational mathematician, I theoretically analyzed the stability of the error propagation rates of the system of partial difference equations that approximated the system of coupled, nonlinear, and time-dependent partial differential equations that governs my initial boundary value problems of extreme-scale computational physics. For my stability analysis, I used the Fourier method of decomposition of the initial errors into Fourier series. I also used the matrix method of stability analysis. Like all stability analysis, mine were also limited to simplified linearized versions of the extreme-scaled problems. That is, I simplified my initial boundary value problem to an analogous problem with constant coefficient and with periodic boundary conditions. I theoretically conducted the error propagation analysis for my partial difference equations of algebra and conducted them by Taylor's expansion. After I had established the consistency and the stability of my partial difference equations, I invoked the equivalence theorem to claim the convergence of the solutions of the system of partial difference equations of algebra to the solutions of the companion system of partial differential equations of calculus. I conducted my consistency and stability analysis both theoretically on the blackboard and experimentally on the motherboard. From my decade-long experience, I knew that the stability criterion for explicit finite difference approximations of the parabolic partial differential equation, such as the heat equation, becomes more stringent as the computational fluid dynamics code changes from 1 to 2 dimensions. It becomes more stringent as the code changes from 2 to 3 dimensions. To avoid such stringent stability conditions, computational mathematicians avoided explicit finite difference approximations that can be massively parallel processed and embraced implicit finite difference approximations that cannot be massively parallel processed. Implicit discretization made sense with the sequential processing supercomputers of the 1940s, 50s, 60s, and 70s. But implicit finite difference discretizations made no sense with the massively parallel processing supercomputers that I was programming in the 1980s. The most popular implicit finite difference approximations were those derived from the alternating direction implicit finite difference methods. Those methods were popular because alternating direction implicit methods yield a set of tridiagonal system of equations, and computational mathematicians love the simplicity of tridiagonal systems of equations as opposed to the messy, dense matrix associated with most systems of equations of algebra. Algebraists loved tridiagonal systems because they can be solved efficiently, as described in linear algebra textbooks. Tridiagonal systems can be solved with small operations count and solved on sequential processing supercomputers. The problem was that tridiagonal system of equations of algebra cannot be massively parallel processed. That is, tridiagonal system of equations cannot be solved at once or solved across an ensemble of 65,536 commodity processors that were identical to each other and that defined and outlined a new internet. Those commodity processors that I visualized as encircling a globe in the 16th dimensional hyperspace defined my small internet. My mathematical discovery that made the news headlines in 1989 and that was reported in the June 20, 1990 issue of the Wall Street Journal was that I experimentally discovered how to solve initial boundary value problems of calculus and how to solve them across a global network of 64 binary thousand computers that define a large internet. That discovery is my contributions to mathematics. I cannot articulate in 60 minutes how I took 16 years to experimentally discover how to massively parallel process and how to do so across 2 to the power 16 commodity processors. If it took me 16 years to understand how to massively parallel process, it may also take you 16 years to understand my discovery of parallel processing. The complete details of my discoveries and inventions are posted as extended lecture series at my website, Emeagwali.com. Mathematics is not a science in its own right. The new calculus that I invented, namely the 9 system of partial differential equations called Emeagwali's equations, is the middle science that mediates between the mind of man and the motion of objects. It's that intermediary position of my new calculus that prompted the debate on whether new mathematics is discovered or invented. I see the 9 Emeagwali's equations as inventions that were abstracted from the discovery of the second law of motion of physics that occurred 330 years ago. That is, my 36 partial derivative terms that I invented were abstracted from the temporal and convective inertial forces that ensures that the sum of the forces is equal to the product of mass and acceleration. That is, the 9 Emeagwali's equations were abstracted from the second law of motion of physics that were in existence for 13.82 billion years, or since the creation of our universe. The physical law that I encoded into my equations existed 13.82 billion years ago. But the mathematical terms that codified those laws could have been known 13.82 billion years ago, but we are not known then. Daalụnụ, afam bụ Chukwura Philip Emeagwali, abụ m onye Ọnịcha. Anyị ga-afụ na emeagwali.com ka o mesịa. I'm Philip Emeagwali at emeagwali.com. Thank you. Thank you. Thank you.
Insightful
Thank you
and
very
brilliant
much.
lecture.